reviewer of many reputed international conferences and journals. He has served on the technical program committees of several international conferences and was the general co-chair of TENCON 2019, the flagship conference of IEEE Region 10. He is the recipient of 2020 IEEE Region 10 Outstanding Volunteer Award. He is the immediate past chair of IEEE Kerala section and currently serving as the secretary of IEEE Region 10. His research interests include synchronization and channel estimation techniques for next generation wireless systems, interference management in heterogeneous networks, special modulation techniques, and deep learning applications for wireless communications.
Thank you, Rehana, for the introduction. With all due respect, may I now invite Professor Samir for the presentation. Thank you.
Thank you, Rehna, for the kind introduction. Let me share my screen. Are you able to see my slides?
Yes, sir.
And in full screen, right?
Yes, sir.
And it is changing also, right?
Yes, sir.
Okay, thank you. Yeah. So, good morning to all the participants of this faculty development program on advanced communication systems research perspective, organized by Department of EC, College of Engineering, Karunagapalli, as part of the Atal FDP program. Communication is a very vast subject, and the organizers have put in various interesting topics covering starting from fundamentals to various advanced topics in wireless communications area in this FDP. And in the morning, you had a session already on some of the very fundamentals required to understand the topics in wireless communications area. Now, being again a first day of the program, I have also oriented my presentation at a bird's eye view level. I will not be going much into the details, but however, I thought I'll just touch upon some of the important challenges people are trying to solve in fifth generation wireless communication systems. And we will also focus a little bit on some of the specific technologies which people are talking about when 5G, as far as 5G is considered. So towards the end of the presentation, we will also look into some, again, a very beginner's view on the sixth generation wireless communication systems people are talking, right? All right. So I've seen that we have a very wide range of participants from across the country, and maybe with diverse backgrounds. So I'll try to keep things as simple as possible. And if you have any queries, please feel free to type in the chat window so that we will be able to discuss those queries at the end of the presentation. Okay. Right. So generally, any talk on wireless communication starts with the evolution of wireless communication. So we'll also just look into the way the wireless communication systems have evolved over the last 4 decades or more, basically, right? So if you can see, though wireless communication has started way back in 1890s when Marconi started his first transatlantic radio wave transmission, and thereafter with different wireless technologies came up. The first major commercial wireless communication system was a cellular wireless system, which was started in 1980s with the first system as the AMPS wireless communication system started in the Nordic Scandinavian countries, and also simultaneously in Japan and other countries. So the first generation cellular, I'm having slight throat problem, so I'll not be If I'm not audible, just please feel to interrupt and tell me. Okay. Okay, so the first generation cellular system, if you look at, there are 2-3 systems, AMPS, TAX, NMT, etc. But all of them used frequency division multiple access technique as the transmission technology. Okay, so where we all know that the users available bandwidth is divided into non-overlapping subchannels, and different users were given these channels basically. And if when a channel is given to a user, whether he uses it or not, it will be fully occupied till the user releases that channel. And the modulation scheme used was frequency modulation, so it was a purely analog system basically. Whereas in after about 10 years, I mean, we have witnessed what is called as 2G. So most of our first telephone system was 2G handset basically. And when it came to 2G, one major change that has happened was the analog systems became digital. And the voice was transmitted. Basically, it was also meant for transmitting voice, but now using digital signal processing techniques. And the multiple access technique became time division multiple access, where the available channel was divided to multiple users at different time slots. And one of the most prominent 2G system was standard was global system for mobile, which was adopted in European countries and later in India. And there was also some experimental systems based on narrowband CDMA, such as IS-95, which was there for some short period of time. I mean, Ambani brothers, the junior Ambani brother Anil Ambani has introduced IS-95 based 2G wireless systems in India as Reliance Communication, and but it could not gain much success basically. And after about 10 years, we have seen the development of 3G. And 3G was again a digital system. And again, there was a drastic change in transmission technology. From TDMA, 3G adopted what is called as CDMA, code division multiple access, right? So code division multiple access was again another paradigm shift, where the entire channel was given to all the users at the same time, okay, but using different orthogonal codes. And these orthogonal codes were designed to have very minimal interferences, and hence users were able to communicate without much issues. And it was also a digital system. And later on, some new variants of 3G came, which was called as HSPA, and high-speed packet access and things like that. But about 2010 onwards, we have been hearing about the word 4G, right? And 4G was promising. And one important change as you go from 1G to 3G to 4G, every time as far as users is considered, is that we were all getting more and more data rate. 1G was analog, 2G was supporting a limited data rate of 9.6 kbps to 13.6 kbps. 3G was able to offer up to 2 megabits per second for pedestrian users, whereas 4G was promising something like 100 megabits per second over wireless communication link, using a new technology called orthogonal frequency division multiple access. But strictly speaking, OFDM was not a new technology at all. In fact, the first OFDM system was proposed, OFDM as a technology was proposed in 1966 by a researcher in Bell Labs called R.W. Chan. But it was not easy to realize multiple carriers using the analog systems available at that point of time. And OFDM was possible when the DFT processors were developed in 1980s. But as a standard wireless communication, it came for as a replacement of cellular wireless communication system with 4G. and various other wireless standards such as wireless LAN, wireless metropolitan area networks, digital video broadcasting. All these have adopted OFDMA very soon because of its superior performance over frequency selective wireless fading channels. Now, 4G. So we'll touch upon a little bit of 4G later. But one thing that we can notice is that ever since 1980s, in every decade, a new wireless communication standard emerged. Right? In 80s, it was 1G, 90s, 2G, 2000s, it was 3G, 2010s, it was 4G. So therefore, maybe from about 2015-16, people were talking about what is called as 5G, and that is basically the kind of standard which is going to come up in the next decade, right? That is the decade that we are living in now. So, what is 5G? So every wireless communication standard or every paradigm shift in the standard has got a vision, right? So the vision of 5G is to connect the entire world and achieve seamless and ubiquitous communication between anybody, that is from people to people, anything, people to machine or machine to machine. And this is very critical. Wherever they are, that is irrespective of their locations, whenever they need, that is anytime, by whatever electronic devices or services or networks they wish, anyhow. So you can see that the vision of 5G is very, very broad. I mean, it tries to connect the entire world, all people and all machines. And not only that, it will communicate between people to machine, people to people, but most of the communication will happen between machine to machine. And that is the key of 5G. And that is the most important challenge, technological challenge as far as 5G is concerned. So this means that we are going to have a very high speed communication. We need to have efficient use of available spectrum. Our communication systems are to be highly energy efficient. And obviously, as far as users are considered, users wanted to get high data rate. So what are the, targets for which people are trying to achieve? The standardization body of 4G and 5G is the same. It is the third generation partnership project, 3GPP, which has basically started as the standardization body for 3G. But it is basically focusing on the development of further standards. So what are the desirable standard that these 5G systems are trying to achieve? Data rate, most importantly. The data rate goal of 5G is 1 to 10 gigabits per second. Now compare it with 4G. The 4G, it was 100 Mbps. So from that, we are trying to achieve a minimum of 1 Gbps, and 1 Gbps was a data rate which was earlier looking, we were trying to achieve from optical fiber communication systems, and that is what we are trying to now achieve through wireless communication using one of the most difficult medium for the transmission of signals, that is the atmosphere, the free space that we have, right? So there are tremendous challenges to be overcome in order to achieve this data rate. And capacity, depending on the, data rate availability, users will be downloading more and more. So we expect a lot of downloads per user. And if you want to support high data rate, then we need to explore higher frequencies. And we also need to use the available frequencies in the most efficient manner. So which means we need to, get new spectrum and better utilization. And we have a lot of concerns about the energy consumption, radiation of wireless systems. And as far as people are considered, But as far as machines are considered, most of the connectivity now are going to have for IoT devices, and they are devices with very small battery powers available. So all these communication should happen with a very low power consumption. So the energy consumption goal is 10% of today's consumption. And in fact, if you look at the base stations, basically worldwide, the out of the entire power consumption of the world, about 3% of power is consumed by wireless base stations. So now you can imagine the kind of power consumption required for base stations, basically. So and that has to be reduced. Latency is very critical. So latency refers to the end-to-end delay for executing a decision, basically. So if you want to have automation, connected cars, and all these applications to take place, then we need to have a very small latency. Latency of 4G was 10 millisecond. Now it is reduced to 1 millisecond. And massive device-to-device capabilities and reliability has to be extremely high, and systems should work in under extremely hostile environments, and the battery life has to be as high as possible for the one-time battery operated devices, basically. And the number of devices per area, it is not really visible. So it is basically 3 lakh nodes per square kilometers. So that is the kind of dense networks that we are talking about. So if you want to realize these goals, then 5G becomes an ultra dense network. And in terms of the reliability and latency, we need to have ultra reliable communications, and we need to have massive machine connectivity for 5G. So these are the research goals, basically. So how do we transform our wireless communication technologies to meet these challenges is the question that is addressed by researchers working in this area. So how do we realize this 5G? So if you look at the data rate support, so data rate is, say, people are talking about 10 Gbps, right? 1 to 10 Gbps. And currently it is basically 100 Mbps. So from 100 Mbps, if you want to reach 10 Gbps, we are talking about 1,000-fold improvement in capacity. So the question is, how do we realize this 1,000-fold of capacity improvement? So there are mainly 3 technical directions researchers have proposed for 5G. Firstly, we know the very famous channel capacity formula of Shannon, where the formula says that the capacity is B log 1 plus SNR, right? So now for 5G, we are trying to redefine this formula as DWM log 1 plus SINR. So SNR has become SINR. That is, instead of signal to noise ratio, we need to compute signal to interference noise ratio, because when you have thousands of devices operated in a very close area, you will have interferences, and we need to consider minimization of interference. So interference mitigation becomes a very critical issue, and accordingly signal to noise ratio becomes signal to interference noise ratio. Bandwidth, yes, bandwidth is required. So we need to explore new bandwidth. So one possibility for capacity improvement is, if you look at the x-axis, it talks about spectrum extensions. That is, you need to explore new frequency band which were not traditionally used for wireless communications, for the commercial wireless communication systems. Also, we need to have efficient techniques to reuse the available spectrum, which means we need to explore technologies like cognitive radio, right? Another strategy is you're going to have more number of antennas, basically. More the number of antennas means more independent data streams can be transmitted over the available spectrum, right? So which means, I mean, we can multi-fold increase the capacity over the available spectrum multiple times. So another dimension for capacity improvement is massive MIMO, that is massive multi-input, multi-output systems. And that is not just traditional MIMO, which was used in 4G, which is basically a 2x4 system or 2x8 system kind of things. It is not like that. We are trying to achieve something like 64 antennas, 128, 256 antennas at the base station, and even maybe 8 or 16 antennas at the user equipment level. The third most important aspect for capacity improvement is multiplication, or having more access points. That is, increase the network density. That is, instead of having a network with one high power base station and user equipments, you try to divide this area into multiple smaller and smaller cells, like micro cells, like femtocells, and further to picocells and so on, so that we'll be able to have small access points in these locations and improve the frequency reuse. As the frequency reuse increases, capacity can be improved, right? So these are the three dimensions in which people are mainly trying to improve the capacity of the 5G networks as compared to 4G. So some of the most powerful enabling technologies for 5G are therefore massive MIMO, cognitive radio, ultra dense networks, millimeter wave frequency bands, and device to device communications. That is, communications between devices, not through any base station or not through any access points. That is peer-to-peer communication when the devices are closely spaced. Right. So now we look into some of these very quickly. I mean, cognitive radio is a very popular term for most of you probably, because we have been hearing about cognitive radio for quite some time. We have different architectures, different types of cognitive radio, like underlay cognitive radio, interview cognitive radio, overlay cognitive radio, with different kind of technologies being used for spectrum sharing. So I'll not touch upon cognitive radio and just look at the spectrum, basically, what we are trying to achieve, what we are trying to explore. So if you look at most of the wireless communication services, like your 2G, 3G, 4G, WiMAX, Wi-Fi, and all these communications, mostly GPS, all these communication use frequencies in the range of something like sub 3 gigahertz frequency. So most of the services use 1 to 2.6 gigahertz frequency. So we are trying to have more data rate, so therefore we need more bandwidth. So one prominent frequency band which 5G is trying to explore is from 2.6 gigahertz to 6 gigahertz, right? So although these bands offer a kind of good frequency band of about 3 gigahertz, okay, with different sub-bands, basically, these may not be sufficient to realize the full potential of 5G, right? So therefore, people are also talking about frequency band in excess of 6 gigahertz. Now, this is called as the millimeter wave frequency bands. However, these frequency bands will have several, issues associated with propagation. Very few studies have conducted on the use of these frequency bands. There are several attenuation issues, etc., etc. But then eventually, these frequency bands will also be explored. So we'll come to that a little later. So now, before that, we will just look into a technology advancement. So if you look at my first slide, so you can see that as we move from 1G to 4G, we have seen a technology change in every generations, from FDMA to TDMA to CDMA to OFDMA. When it comes to 4G, in the uplink, in the downlink, we have used OFDMA, and in the uplink, we have used a modified form of OFDMA called single carrier frequency division multiplexers, that is SCFDMA, which is a slightly modified, one more FFT is taken in the transmitter side to reduce the peak to average power ratio. What is the feature of OFDM which is used in 4G? We were dividing the available frequency band into multiple subcarriers, and these subcarriers were allowed to overlap in frequency domain, so that we'll be able to pack more subcarriers into the available bandwidth, and therefore more data rate can be achieved. However, we were doing this by maintaining the orthogonality of the signals in the time domain, so that at the receiver we were able to separate these signals without any interference, as long as the synchronization and channel estimation, etc., are very good. The advantage was that, say for example, when we divide the number of available bandwidth into large number of subcarriers, like say 64 or 128, we were able to support large number of users, right? If say we are giving 2 subcarriers to one user, 3 subcarriers to another user, we were able to effectively communicate large number of users data over one OFDM symbol. And because of the inherent advantages of OFDM, the frequency selective channel becomes a frequency flat channel, and we were able to get a lot of advantage. Now, when it comes to the LTE standard, that is the 4th generation standard 3GPP Relay 16 standard, which is basically the LTE advanced, they define a physical resource block as the basic unit of allocation, which comprises of 12 subcarriers in the frequency domain amounting to 180 kilohertz. And a subframe was defined to be having 14 OFDM symbols, and multiple resource blocks can be allocated to user in a given subframe depending on the user's requirements. So these are some of the, I mean, the frame structure, etc. And the advantages was that, I mean, the users who are paying more, or users who are having more quality of assurance, was giving good quality subcarriers. Some of the subcarriers, sometimes the channel associated with this subcarrier is bad, channel associated with this subcarrier is good. So if a user is paying more high priority, then the user will be given these good subcarriers, and the other users will be given bad subcarriers and all. So in 4G, if you look at your data pack, okay, so when your data pack is active, you will be given good subcarriers, and when your data pack is, hello, yeah, when your data pack is not active, then you will be given subcarriers whose channel conditions are poor, so that your data rate will be less. So that is the kind of priority that was given. Now, one of the most significant feature of these all traditional orthogonal multiplexer systems, all FDMA, TDMA, CDMA, or FDMA, all are considered as orthogonal multiplexer systems. Now, its feature is that it basically allocates a particular subcarrier or a particular channel exclusively to one user, and at that time that channel is not given to any other user, right? So if I am giving this subcarrier to a user, say first subcarrier F1 to a user, as long as a particular user is using it, I will not be giving this subcarrier to any other user. So that is the basic principle of any orthogonal multiple access technique. In TDMA, if a time slot is given, as long as a user is using the time slot, that time slot is not given to any other users. Simple. That is the, even in CDMA, it is like that, because if a code is given to a user, as long as a user is using that code is not given to any other users. And that is called as orthogonal allocation of resources or orthogonal multiple access technique. And in that way, all the multiple access techniques which are used till 4G are orthogonal multiple access techniques. Now, we are going to see a very important change in 5th generation wireless systems. Because in 5th generation, we need to accommodate large number of devices, large number of connected devices, and also to support high data rate, right? What we do is we multiplex users on the same frequency resource. So eventually your multiple access technique is going to become what is called as non-orthogonal multiple access technique, NOMA. So if you have gone through literature on 5G, you may be able to see a lot of literature on NOMA. So what is NOMA? In NOMA, in simple terms, say suppose I have say 2 users, I'll try to, and the NOMA can be used along with OFDM also. So suppose I'm using NOMA here, then along with one user allocating this subcarrier to allocated to one user, I'll allocate this subcarrier to one more user, same subcarrier. Okay, in simple terms. So then now how do we manage this? Because when 2 users are trying to communicate over the same channel, you'll have severe interference, right? So how do we manage this? So this is managed by, pairing of users in some clever way. That is, pairing users enjoying good channel conditions with users suffering from poor channel conditions. And it is decoded at the receiver by using what is called as successive interference cancellation type receivers, which is basically used in spread spectrum systems earlier. Okay, so that is one of the techniques. So in simple terms, the idea is like this. If we say if I have 2 users, M and N, and I try to allocate the same frequency at the same time to these 2 users, but they communicate at different power levels. You can see that the power of user M is more than user N, right? So the user M is considered as a far user and user N is considered as a near user, right, to the base station. Okay, so the near user is given with less power. So what will happen? He is having a kind of good channel. So at the user N, user M's signal will pose a great level of interference. So before decoding the signal for user N, I will try to decode the signal of user M and then subtract the signal from the composite received signal and then decode the signal of user M. That is, at the near user level, the signal of user M is decoded first and removed from the composite signal and then decoded, right? Using successive interference cancellation. That is the technique which was prevailing, a few years back now. People are working on better detection techniques, basically. One of my students was also working on developing better detection techniques for this problem. Now, as far as far user is considered, far user's channel is bad. So by the time the signal is received, the signal of far user is having high power, right? And it is coming along with the signal of the near user who is having a low power. By the time it travels over this bad channel, the signal of user N will be, felt like a small interference to the signal of user M. And the user M will decode its signal in the presence of that interference, or will use some kind of interference minimization technique, and then simply decode user M's signal without going for any successive interference cancellation, because by the time the user M gets that signal, it will be user N signal will be coming as a weak interference to the user M's original signal. So this is the, basic idea of norm. Okay, this is with 2 users, and if you are having more users, then accordingly you may have to adjust the power levels and do successive interference cancellations. So this is called as power domain norma, and this norma can be implemented in different domains. Like a code domain norma is also very popular. Like instead of sending these signals directly, we can send the signals using different spreading codes, like we have done in CDMA, which is called as the code domain norma. So you will be able to see several interesting ideas and technique and research challenges associated with norma from this paper. This is a very good paper on non-orthogonal multiple access techniques for 5G. It's a review paper, and if you're interested to work on this area, then please go through this topic. Now, I've discussed this actually. So, how do we make use of norma? How norma is considered as an ideal solution for 5G? One of the most prominent, so in 4G, it was OFDMA. When it comes to 5G, one of the major technological changes is norma. That is, norma is considered as the prominent multiple access technique for 5G. But norma can be implemented on a CDMA system or an OFDMA system, so that it will come as an additional technique to increase the spectral efficiency and thereby the data rate of the communication system. So let us consider 2 scenarios. If one user has a very poor channel condition, okay, and if we allocate orthogonal if we use orthogonal multiple access, then the resource allocated to that user becomes a waste, because that user may not be able to utilize that because of the poor channel condition. Whereas here, we can overcome that by sending another user's signal over the same frequency. So we can make use of the available spectrum efficiently. And also another very important advantage as far as 5G is concerned, 5G has to serve a lot of IoT networks. And IoT networks will have very low data rate, right? And if I allocate orthogonal multiple access techniques, the available resource may be much more than what is required to transmit a low data rate signal of an IoT device. So whereas if I use norma, I can support the transmission of multiple IoT devices over one resource block, one subcarrier, say, using norma. So that is why norma is considered as a very important candidate for supporting 5G. And it is not going to be norma alone which can give you the kind of capacity improvement that we have discussed earlier. So we need to have multiple technologies to be used in conjunction to achieve the kind of data rate that we have talked about. So one such technique is by using what is called as clustered norma. So norma itself is not applied directly. We use a base station with multiple antennas, kind of a massive MIMO system, where which will explore what is called as the spatial diversity. That's what is spatial diversity. If I transmit a signal in this direction, then I can use that bandwidth. In the same bandwidth, I can transmit signals in another direction, signal in another direction, signal in another direction, with minimal interference between these transmissions. Okay, so which means that the same resource block, same channel can be reused at multiple spatial locations. And in each of these spatial locations, I can combine large number of users by using NOMA. So that is called as clustered NOMA. That is, within a spatial region, I'll support large number of users in that available spectrum by means of NOMA. So that way, I can increase the number of users that I can support in a cellular region. And again, it is not sufficient. This is not sufficient to realize the capacity improvement and connectivity required for 5G. And that is where we have another very handy tool coming in, which is called as heterogeneous networks, or popularly called as HETNet, in combination with NOMA. Okay, so this is a very powerful tool. What is a kind of, femtocell network? Femtocell networks are popular earlier also. Like instead of having a single base station serving the entire users of a cell, okay, we divide this cell into multiple smaller cells as well, and then we use low power base stations in each of these smaller cells, okay, and the same frequencies which are used in these bigger cells will be reused in these cells. That is the basic idea of picocell, femtocell, all these kind of structures. Now what is going to come? Now what is being told, explored is the use of NOMA in this architecture. That is, we divide the available spectrum, available space into multiple, regions within a cell called femtocells. And each of these femtocells or picocells will be served with small low power base stations, and they will be supporting the users using NOMA. Okay, and users, and they will be using the same spectrum which are being used by the macro cell, right? And the users with high mobility and all will be supported by the macro cell using massive MIMO and all. And clustering also is explored here, okay? And here we support large number of users. So both HETNet and NOMA have the prime objective of promoting high spectral efficiency. Now, what is the biggest advantage? Indoor coverage enhancement, increasing capacity, offloading of the overlay macro cell traffic. This traffic can be offloaded to a great extent. By combining NOMA into this, we allow data transmission by multiple users in the same resource block. But the most important challenge is that the crosshair interference, because the same frequencies will be used by this macro cell and these picocells, okay, and therefore the macro cell users will be causing interference to the picocell users, and they themselves have their own interferences. So therefore, this crosshair interference is the interference caused by macro cell users to femtocell users, and similarly, the femtocell users back into macro cell users. Is the biggest challenge of employing NOMA HETNess. So this causes severe performance degradation due to the high transmit power of undesired microcell users in the femtocell tier. This is more significant in the femtocell tier. So hence, efficient interference management is essential to reap the benefits promised by the NOMA HETNet combination. Now, what I'm going to tell is a kind of research which we have, we have been working on. Just to show, this is not to show anything, but just to show how a research problem can be formulated, or research problem is formulated. Really, okay. So when we looked at the literature in around 2016-17, looking at that review paper which I have mentioned and all, we have seen that most of the works focused on downlink norma, that is from base station to user equipment. So in downlink norma, the received superimposed data of all the users is is only a function of its own channel state information. Whereas because all signals are coming from base station, whereas in uplink norma, the base station requires the desired users and interfering users channel state information for decoding the norma users data, because the entire CSI is required for successive interference cancellation, which is required to be done at the base station. And also very complicated user pairing and power allocation are required to ensure differentiation in arrival of power. I mean, the power level, the separation is in the power level. So a lot of information is required to be exchanged between user equipment, that is mobile station, mobile phone, and base station to decide what is the optimal power level to be used. So all these causes severe overhead. And acquiring the interfering users channel state information at the base station receiver is difficult in practice because of the limited backhaul capacity, the backward network capacity. So therefore, it was difficult to design spectrally efficient norma scheme without requiring the macrocell users channel state information at the base station as far as uplink HeartNet was considered. So therefore, uplink HeartNet was not very well explored at that point of time. That is 2017-18. That time we were not seeing any literature as such on uplink HeartNet except for some one or two papers. Whereas most of the works were focusing on the downlink. Downlink, the job was pretty easy, right? So therefore we proposed a kind of an uplink system, uplink norma system, where more priority is given to the femtocell tier. So we consider the femtocell users as the desired norma users and the macrocell users as unwanted norma users. And the decoding of femtocell users was required to be done from the composite received signal comprising of both femtocell users as well as macrocell users signal. But macrocell user signal is considered as an interference. So while decoding the femtocell users, these interference coming from macrocell users are to be minimized. So when we explored this, we have seen that with successive interference cancellation, it is extremely difficult to do this because we need to know the channel state information of all the macrocell users, which was very difficult to get at the femtocell base station. So therefore, we worked on it and finally we proposed a few techniques based on new projection operators, which decompose the desired norma user signal and interfering user signal from the composite received signal. The combined received signal, we applied certain projection operators, right? We used the vector space concepts there, applied a projection operator there in such a way that the signal, composite signal, is decoupled into two different streams. One is the desired signal and the other one is interfering signal, and accordingly then we will be able to filter out the interference signals. And this was the idea. And so if you look at the signal model, I mean, I will not go into the details, don't worry. Okay, so I'll just tell you what is the problem so that you can also work if you are interested on this particular problem. I'm telling you the problem basically. I'm not going into the solutions basically. Okay, so the idea is this, that we'll have a cellular architecture heterogeneous system with one macrocell base station and multiple femtocell base stations. And if I consider one such femtocell base station, there the signal received at this femtocell base station, that is here FBS1, would be, okay, the superposition of the signals of all femtocells. That is the norma user's signal in this femtocell. That is its signal, channel, and the power amplitude basically. Okay, That is this the combined signal of the desired users, and this is what is to be separate. But this comes along with what? Firstly, interference from other femtocells. There are one femtocell, another femtocell, another femtocell. So this is all these femtocells are using the same frequency mapping. So they will be causing some interference, and this interference is called as the co-tier interference. Okay, other femtocell users. Okay, from the same tier, from the same femtocell tiers, you will have a certain number of femtocells, and they will be having some interference. Then we have a macrocell base station. Then interference from these macrocell users, MU1, MU2, MUM. So that is this term, and plus the omnipresent additive white Gaussian noise. Okay, which is always there. So you have a very complicated signal here, which is a superposition of the desired signal plus co-tier interference plus cross-tier interference plus additive white Gaussian noise. So we need to design an operator which can separate out this with very minimal components of this and this, right? So we have worked on this, and just to show the outcome, if you're interested, you can go through some of these papers to see what all things we have done. So we have in fact developed a QR decomposition based technique for separating this interference and decoding the signal. And then we have also made an oblique projection based NOMA scheme and under imperfect and perfect CSIR, and which was published in IEEE Transactions on Vehicular Technology. And there are some other papers also. So all these are basically different ways in using different assumptions and conditions we have solved this problem. Okay, and but there are a lot of possibilities still exists for working on this area. So this is just to show one problem and how do we solve this problem, how do we model this problem. So this modeling is the most important part, and once this model is available, then we can try to see how we can apply suitable mathematical techniques to solve this problem. Okay, so this is one type of, and this R NOMA technique does not require techniques, none of these techniques require successive interference cancellation. So that was the main feature of our technique, basically. So we worked on proposing different variants of NOMA, okay. So, but there are various other directions available for this area, like finding new coding and modulation for NOMA, hybrid multiplexers, how to combine other multiplexers techniques with NOMA, how user pairing and clustering can be done in an efficient way, how cooperative communication concepts can be integrated into NOMA, how users can cooperate and communicate, interplay between NOMA and cognitive radio. Cognitive radio can also be explored along with NOMA to improve the spectral efficiency further. Impact of CSI and limited channel feedback. Security provisioning, because the near user will be able to decode the signal of far user, which should not cause any security issues. Okay. And various other hardware implementation issues and other synchronization issues, frequency offset, high mobility channel issues, etc., of NOMA. Okay, so that is about NOMA. And another very powerful enabling technology for our high data rate communication system of 5G is massive MIMO. We'll not go into the details, but just to show again, we have been talking about MIMO from 3G onwards. 3G used a very simple type of MIMO called Alamotti code. Okay, you might have heard about this. And when it comes to 4G, 4G used what is called as 2x4 systems and 2x8 kind of MIMO systems. But now what we are talking is a massive array of antennas. A very large antenna array will be used at each base station, and the order of magnitude of antenna will be much larger, and which means that a large number of mobile users can be served by means of the same spectrum, and that is the most important advantage. So there are a lot of challenges also, because if I want to decode the signals of all these mobiles in the uplink, then I need to know the distinct parameters, the channel, carrier frequency, offset, etc., which are estimated using the pilot signals. And these pilot signals will be corrupted because of the large number of antennas. Every antenna will be capturing some portion of the signals of other users as well, which is called as a pilot contamination. So how do we estimate the parameters with a contaminated pilot is a very important challenge. Okay, so how do we achieve this? And there are techniques based on time division, duplexing, code division, multiple access, etc., for reducing pilot contamination. But the kind of promise in capacity improvement that can be achieved from a massive MIMO is tremendous. Okay, so as an example, if you look at the sum rate in the uplink and downlink, okay, with one cluster itself, this is one cluster. Earlier I have shown clustered MIMO basically. So this is with multiple clusters, 1, 3, 8. So just you look at the black plot in the uplink, okay. So as the number of base station antennas increases, the sum rate is bits per second per hertz, which means the number of bits that you can transmit in 1 hertz of bandwidth. So that increases from something like 12 to 24 as the number of antennas increase from 24 to 168. And this is huge. What you can see is, if you just compare it with your single input, single output conventional communication system, say QPSK, right? In QPSK, what is the sum rate? In 1 hertz of bandwidth, you will be able to transmit 2 bits of information, right? And if I use 64 QAM, then in 1 hertz of bandwidth, I'll be able to send 6 bits of information, maximum, that is 6. Okay, whereas here with multiple antennas, we are able to transmit something like 24 bits per second per hertz. That is 24 bits in 1 hertz of bandwidth with a 168 base station antennas. And that will increase to something like 45 when you use multiple clusters. Similarly in the downlink as well. Okay, so therefore the kind of capacity improvement that MIMO can provide is enormous, and that is one of the most important most important feature of MIMO. But if you want to achieve this, there are several challenges as well. There are a lot of research problems associated with massive MIMO. Some problems people are already working on these. Some are difficult, some are relatively easy, and so on. So some of the problems are like this: channel measurements and modeling, okay, the implementation aware algorithmic design. This is a very important topic. That is, depending on the dynamic configuration change of multiple antennas, how the systems can take care of its parameters. I'll come back into this towards the end. So exploiting the m-k excess degrees of freedom. That is, if I have m number of antennas and k number of users, where m is much larger than k, how can I use that additional m-k antennas, okay, for the either it can be used for increasing the diversity gain, or it can be used for increasing the data rate. So how we can trade off this basically? The MAC layer design, power control issues, the distribution, pilot contamination issues, so all these and the system level coexistence with heterogeneous networks and device to device, which doesn't require any cellular architecture. Okay, so and massive MIMO in millimeter wave frequency band. That is another very important area, because we will come back into come to millimeter, and massive MIMO is considered as a very important technology for millimeter wave frequency bands. Okay, so if you look at the 5G spectrum in the sub 6 gigahertz frequency band, which is the prominent or near future 5G, will be operated, will be given in this, but will be standards will be operating in this frequency bands. In India also, you can see that we have 3,300 megahertz to 3,400 megahertz, 100 megahertz bandwidth is given for 5G, and different countries have given different bandwidth, and this forms only a very small portion of the 5G spectrum. You can see that this is a kind of spectrum which we are already given, which is basically a spectrum which coexists with 4G, whereas 6 to 100 gigahertz is treated as the millimeter wave frequency bands, and this frequency band will offer extremely large potential for transmitting signals. But since it is transmitted at millimeter waves are having several issues. Most importantly, they experience severe attenuation in the presence of water molecules, oxygen molecules, etc. So if you look at the spectrum attenuation versus frequency, you can see that some spectrum, at some frequencies or wavelengths, you can see are severely attenuated, these frequency bands, whereas some are not that attenuated, moderately attenuated. So we try to use these frequency bands which are less attenuated for our communication purposes. So that itself offers huge bandwidth. But since these are having high attenuation, their range is limited. So mostly millimeter wave will be used for communicating in the near vicinity between devices operated at a very small geographic area. Like henceforth in 5G, all your gadgets will not be connected with wires. They will be having a high-speed Bluetooth. This high-speed Bluetooth can be enabled using millimeter wave, or local area networks can also be enabled. Wi-Fi can be enabled using millimeter wave. So there are a few commercial standards which are being explored using millimeter wave. 802.15.3c, which is for indoor personal networks, 802.11ad for wireless local area networks, and so on. So these are some of the 802.16.1 for fixed point millimeter wave access. So these are some standards which are basically trying to explore millimeter wave for the next generation wireless systems. So there are several challenges associated with millimeter wave because it is very sensitive to attenuation and blockage. And the advantage is that since the wavelength is very small, we know that the minimum separation required in terms of wavelength in a MIMO system is lambda by 2. So when lambda becomes smaller, lambda by 2 becomes smaller, and therefore we'll be able to pack more antennas at the base station or access points. So therefore, we have an advantage of using massive MIMO with millimeter wave frequency. So if you summarize the challenges associated with millimeter wave bands, it is challenges due to topology, sensitivity to blockage, challenges associated with the wavelength, attenuation, etc. So there are different areas in which people are working on this, the bringing out new topology for millimeter wave devices, directional beamforming, stochastic blockage modeling, and these are some of the topics which people are working. So I mean, there are a lot of, only very few people are working in this area. Rappaport, who has written a book on wireless communication. So one of his main research area now is to propose channel models for millimeter wave frequency bands. So he is doing extensive experimental studies to bring out new channel models for millimeter wave frequency bands. Okay, so to summarize our discussions on 5G, simple magic formula for achieving the high throughput is basically, the new definition of throughput is throughput per square kilometer. So what is the bits per second per square kilometer that we will be able to achieve? And that is a function of the available spectrum, the number of cells that we use, the cell density, that is the division of macro cell into femtocell, picocell, nanocell, etc., and the spectral efficiency of each of these cells, that is bits per second per hertz per cell. Okay, so if I have to achieve this 5G goal of 1000 times improvement, then the target goals from each of the three techniques is, with the help of available spectrum, we are trying to achieve a 3x improvement in efficiency, data rate. Okay, with the help of improving techniques to reduce interference or spectral efficiency, like new technologies like NOMA and things like that, massive MIMO, NOMA, etc., we are trying to achieve a 6x kind of improvement in data rate. Whereas the maximum data rate of is going to be achieved by means of heterogeneous networks, that is higher and higher cell density, and we are trying to achieve a 56x kind of improvement. So together we can see that 3 into 6 into 56 will be 1000, right? So these small cells and associated interference management techniques and multiple access techniques, etc., is going to be a very key enabling technology for 5G, right? So this offers tremendous potential for people like us who are interested in working on some of these technologies, and through ourselves, through our students, and we'll be able to come out with some contributions which could be useful in achieving this 1000x improvement in data rate that is promised by 5G. Nevertheless, some experimental systems in 5G are already in place in different countries, like Korea, Japan, USA, and probably by 2022 we also may get some experimental systems. But by 2025, 5G will get mature. Like by 2014-15, 4G almost got mature. And but then all the 4G, all the 5G that we are going to get in the near future will be 5G in the sub 6 GHz frequency band. 5G in the real sense, or the kind of 1000 times data rate improvement can be achieved only through millimeter wave frequency bands. and that requires several challenges to be solved, and that will take time basically. So that opens up several possibilities for research. And I'll take a very small break now, maybe about 5 to 8 minutes, okay? And then we'll come back into the remaining topics, which is on, say, 6G.
Okay, sir.
Okay, thank you, sir. We'll have a short break. We'll rejoin at 12:40. Thank you.